Cominciamo la sessione con Anna Painelli e spero che lei mi introdurrà su argomenti.
No, questo.
Sì.
Allora, buongiorno a tutti. Grazie dell'invito che è stato molto gradito. Questa piccola conferenza italiana è sempre gradevole da seguire. Oh, I have to switch to English, mainly because there is at least one non-Italian speaker here. So I was just thanking the organizer at this point. Okay. Okay, I will try to discuss this morning a kind of vibrational spectroscopy. So in this sense, I'm in line with some of the interesting points in this conference. Of molecular materials, again, I'm more or less in line with the main topics in this conference. But it is a sort of strange vibrational spectroscopy because it is real-time vibrational spectroscopy, and I will introduce it immediately. And also the molecular materials are a sort of strange for this audience because they are molecular crystals. So crystals with periodic structures and things like that. Okay. So let's start with a short introduction to this ultra-fast spectroscopy. I have a laser pointer somewhere. Okay, so the basic idea, okay, no, it is too weak. The basic idea is that you start from from your ground state, but then if you have a very fast laser pulse, you can excite your system, but if the laser pulse is, the length of the laser pulse is shorter than basically half of a vibrational period, you can excite a coherent state on the excited state, a coherent vibrational state, and this starts to oscillate back and forth on the potential energy surface. And then whatever probe you shine on your system to measure whatever kind of response, the response, in this case induced transmittance, will show some noise, which is not actually a noise, it is an oscillation, which reflects, of course, this oscillation. And in fact, if you take the Fourier transform of this signal, you have 600 centimeter to -1, which is a vibrational frequency. So this is, I feel, fascinating because it allows you to look, to see vibrations in the real time, okay? This is one of the first experiments, so you see this a few years back at this point. A chromophore in solution. Very recently, this year, we were able to, at last, publish a paper on this topic, and we are simulating these coherent oscillations using our machinery of essential state models. And for this kind of molecules, which are a very simple system, we were able to demonstrate quite impressive effects of inhomogeneous broadening due to polar solvation. But possibly what it is more interesting is what happens when you have system like this die here, where the first excited state shows a symmetry breaking, so a B-stability, or call it as you want. The question we were asking is, when we excite this system, we are in a potential energy surface which is strongly enharmonic, of course, but also we are a very close excited state here. So not only the harmonic approximation breaks down, but also the adiabatic approximation breaks down, and so what happens in this system? And I don't want to spend too much time. This is basically the potential energy surface of the ground state. The red, this red thing around the that you see is the coherent wave function, and the two green circles are the minima of the excited state potential energy surface. And so what we can do here is to see what happens at the wave function And this is pretty trivial in a sense. It is what you have expected, possibly, but I want to stress that it is a truly non-adiabatic and non-harmonic calculation, and it was not obvious from the beginning that we could be able to do that. In any case, this was just to show you what we can do with our favorite machinery of essential state model, but today I will stick on a different topic, so molecular crystals and these photo-induced ultra-fast coherent oscillations in these molecular crystals. So my talk will go very quickly with a description of the material, which most probably you are not familiar with, then a motivation why the material is interesting to me, and then the model. Then I have to convince you that the model works, so I will do that discussing some sort of old stuff, couples of years, not so old, on vibrational spectra of this, so ground state vibrational spectra of this system, and then I will go to coherent oscillations at the neutral ionic phase transition. And I hope I will be able to share with you the enthusiasm I feel about this result. Okay, before I forgot, the people who did the work, mainly students. So vibrational work on the ground state was mainly due to Gabriele Davino, a former PhD student, one of the most talented PhD students I ever had. And then I was very lucky because I had a very talented undergraduate student, Lorenzo Cavatorta, who did all the work on photoexcited coherent oscillations. And of course, this work is also done in collaboration with experimentalists in my lab, Matteo Masino and Alberto Girlando. And a couple of international collaboration for the theory part, Zoltan Sus in Princeton, and for the experimental part, Martin Dresser, Aldo Brillante, and Marie Lemecq in Grenoble. Okay, so now very quickly to the material. I will try to go towards this. The material, it is a molecular crystal made up of very simple pi-conjugated molecule, which have a strong electron donor and acceptor character. This is a prototypical material, TTF chloranil. The point is that if you are lucky, these two molecules form stacks, one-dimensional stacks, where the molecule alternate, donor and acceptor, donor and acceptor. And the point is that there is an overlap, non-negligible overlap between frontier orbitals along the stack, so you have delocalized electrons in 1D, basically, while there is no overlap in 3D, of course. There are interactions in 3D, which are, of course, electrostatic interaction. You cannot neglect that. But the most important interactions, the delocalization, is one-dimensional. And because of electron delocalization, of course, there is a rearrangement of charges on the molecular sites. So the molecular sites bear a positive and negative charge, a fractional charge that we will call rho. And materials are known with the rho of the order of 0, and this means you have a very weak. And so neutral molecules, so you have a lattice of molecules which resembles anthracene, so a molecular crystal. But there are systems where you have very strong donor and acceptor molecule, where rho is of the order of 1, so you have ionic crystals, so something similar to sodium chloride in a sense. And what it is even more interesting is that in some systems, and TTF chloranil is among them, you have the possibility to switch the system from a neutral to an ionic state, and this is what is, sorry, I made a mistake, what is called the neutral ionic phase transition. And well, it is induced, as it is shown here, by temperature, but also by pressure, and the physical origin for that is very simple. When you compress the lattice by either decreasing temperature or increasing pressure, you increase electrostatic interactions and favors charge transfers, favor ionic states. There is another peculiarity of this system, which is the lattice instabilities. The neutral system, in the neutral phase, the system is stable as a regular lattice, but when you go towards an ionic phase, there are both experimental and theoretical hints, or demonstrations, say, that the system becomes unstable and dimerizes. Okay, so you have two equivalent states with positive or negative dimerization, but the stacks always dimerizes. And this is very interesting also from the applicative perspective, because these dimerized stacks are potentially ferroelectric. And indeed, the TTF chloranil was demonstrated as a true ferroelectric system in the low temperature or high pressure phase. And of course, the ferroelectric systems are very interesting in many perspectives. Okay, this is TTF chloranil, but as I told you, there are many other systems. If you put two metal groups, you can grow dimethyl TTF chloranil crystals, and in this case you have continuous phase transition. So you can have either continuous or discontinuous phase transition. Today for us, discontinuous phase transitions are more interesting, because if you have a discontinuous phase transition, of course, you have a region of multi-stability for your system. When you have a discontinuous phase transition, you can have hysteresis, so you have metastable states. And the idea is to photoinduce a phase transition by simply optically populating this metastable state, long-lived metastable states. And this is possible and has been demonstrated for TTF chloranil. And this is again something which is very interesting from an applicative perspective, because this tells you that you can use light to switch ferroelectricity in this kind of materials. And this, of course, makes everything more appealing. Okay. So I hope you are already happy with the motivation, ferroelectricity at least, and photoinduced ferroelectric phases. But there are many other properties which are interesting in this system. Again, ferroelectricity, photoinduced phase transition, but quantum phase transition occurring at very, very low temperature have been demonstrated here. Another very interesting result, experimental and theoretical result, is the dielectric anomaly. In this system, which are organic molecular crystals, so like anthracene in a sense, there are no heavy atoms, nothing, you can reach a dielectric constant of the order of 600 or 800 or so, which is really unusual. And okay, and then very recently there are hints of room temperature organic ferroelectrics, but I must say I don't believe too much this result, even if it is a Nature paper, or possibly because it is a Nature paper. And there are a few hints of multiferroic behavior. These are really interesting to me. Okay. There is also some interest, more fundamental interest, because we have delocalized electrons in 1D, but the bandwidth is extremely narrow, so we have strongly correlated electrons, really strongly correlated electrons in 1D on a soft lattice. This open the possibility to work with a fascinating system, with a fascinating physics, having a sort of toy model, which is, as it is always the case, what interests me. Okay, now the model. Again, the model will be the simplest model possible for this kind of system. And of course, if you have strongly correlated electrons, you will, in 1D, you will stick on the Hubbard model. So what I have here is T, the hopping integral between nearest neighbor sites, U, which is the repulsion of two electrons on the same site, and then there is something more because I have a specific system, so there is on-site energy alternation here and electrostatic interactions in 3D there. I can take advantage of the chemistry of the system, so doubly ionized sites are very high in energy, and simply putting U, the Hubbard U to infinity, so extremely correlation regime, I can get rid of these states because they acquire they have very large energy, and stick on this kind of excitation, which is at fixed energy gamma. So the Hamiltonian reduces, but what reduces is the dimension of the bases, because I'm killing down a few states. And this is the electronic Hamiltonian. Not enough, I have to include the phonons, the vibrations. And first of all, the dimerization phonon, the one that drives the dimerization. It is coupled to the electrons because it modulates T, so this is the pious coupling, basically. And this is the elastic energy, of course. Then I also introduce phonons modulating on-site energy, so these are molecular phonons that modulates on-site energy, so again, linear coupling and elastic energy. And I want to stress immediately and strongly that the phonons and vibrations that I introduce in my model are strictly harmonic. We will see wildly anharmonic potential energy surfaces, but the anharmonicity is not put in by hand in my model. It is a result of the coupling between electrons and phonons. Okay, my phonons are harmonic at the beginning of my discussion. How to deal with this Hamiltonian? So this is the complete Hamiltonian. I have to make some approximation, of course, even if the Hamiltonian is comparatively simple. The first one is to reduce everything to a one-dimensional problem, adopting a mean field approximation for interchain interaction. Just electrostatic, you can do mean field. The second approximation is, of course, the adiabatic approximation. We are forced to that because in a solid state you cannot do anything more, or, well, it is very hard to do anything more. So I solve the adiabatic Hamiltonian, the electronic Hamiltonian as a function of Q and delta. And how do I treat this kind of Hamiltonian? I will resort to brute force diagonalization, which amounts to a full CI in your language. And what I can do are one-dimensional chains with periodic boundary conditions up to be really strict 18 sites, not 20. 20 is not possible to me, at least. The trick to do that, it is already a big system, okay, because it is a full CI. The trick to do that is the diagrammatic valence bond technique. So I will work in the singlet subspace, considering only K equal naught, so only zone center, Brillouin zone center states, because are the states which are relevant to spectroscopy, optical spectroscopy, and to phase transition. So, I have adiabatic approximation. The first result I can show you is the ground state energy as a function of the coordinate, what everyone calls potential energy surface. Please look at how anharmonic the system is. We started with harmonic phonons, but the result is wildly anharmonic, and the reason is the coupling with the electrons and the proximity to a phase transition. We are near to a phase transition, but the system is stable as a neutral regular stack, delta equal naught. If I take the same model and increase a little bit the electrostatic interactions, you see that the shape of the surface changes, and I now have two minima, plus and minus delta, which correspond to the ionic dimerized phase. What's in between? For this model parameter, I get multi-stability. So I have a system where a neutral regular stack and the two equivalent ionic dimerized stacks do coexist. And this coexistence regime, of course, points to a discontinuous phase transition. If I use quite a sort of different model parameters, I can, of course, go from a neutral to an ionic dimerized phase continuously. So I can model either continuous and discontinuous phase transitions. So this already tells us that the model works. But I would like to have more specific and more detailed comparison, and I would like now to address vibrational spectra. So we'll start with the experiment. The experiments are from my lab, Matteo Masino and Alberto Girlando, as I told you before. So this is a Raman spectrum in the region of molecular vibrations, so the region where, of course, molecules oscillates. Inner vibrations of the molecule. And there is already a phenomenon that it is well known and it was understood since many years at this point. You see that the frequency of the mode goes down softens, spectroscopy says softens, when you go towards the neutral ionic phase transition. This is again due to the coupling of electrons with phonons. But this was really well understood since many years because it can be understood in the harmonic approximation, and almost everyone is able to do harmonic calculations. More interesting is what happens in the infrared spectrum. In the infrared spectrum, the red lines, you see that at the red and blue side of each Raman band, you observe what we call the side bands. What side bands are, of course, spectroscopists know, they are combination bands. And these combination bands are the combination of a molecular vibration, 1000 centimeters to -1, with a lattice vibration of the order of 50 or 20 centimeters or -1. This means that there is a huge anharmonic coupling because you are coupling modes with very large frequency difference, very large difference in frequencies. So here appears a combination with the lattice mode. This is dimethyl TTF chloranil. The same occurs in TTF chloranil. There is a result I want to show because I'm very happy about this result, of course. From the analysis of the spectra, I can get information about the frequency of the lattice mode in the far infrared region. So it goes from 60 to 20 centimeters to -1 or something similar. Nice. What it is even nicer is that this data coincide, the red dots, with similar results that can be extracted from the analysis of diffuse X-ray scattering spectra. And this is quite interesting, and we were able to publish the PRL a few years back because people measuring diffuse X-ray scattering were giving a completely different explanation, very fancy one, very popular, including defects, states, and things like that. We were able to demonstrate that a soft mode can do the job. Okay, get back to this. Combination bands are a signature of strong enharmonicity. Can I calculate these spectra? How can I calculate these combination bands? If I want to do some vibrational spectroscopy, fully relaxing the harmonic approximation, this strategy could be time correlation functions. So everyone knows that infrared absorption and non-resonant Raman scattering can be calculated from the Fourier transform of the correlation functions of depolarization, the dipole moment, and depolarizability. And of course, to do that, what you have to do is, first of all, the dynamics of your system. But the dynamic in the ground state on a two-dimensional surface is a very simple trick. And of course, we can do that. This is just a cartoon for showing that I'm able to use PowerPoint. But of course, you can do classical dynamics in these anharmonic potential energy surfaces. The tough part is the calculation of depolarization and depolarizability on these surfaces because you want their evolution, not the evolution of the coordinates. This can be done using a trick due to an approach due to Raffaele Resta, who was able to demonstrate that in extended system, the polarization can be calculated in terms of a Berry phase. So there is this very famous expression. A few years later, together with Zoltan Sus, we were able to extract a closed expression for the polarizability based on the same equation as Resta for depolarization. Just to show you two beautiful pictures, I'm not sure you can appreciate them. This is the polarization on the Q delta plane, and this is the polarizability. You see they are very, very strange, and again, the reason is that we are in a system with strongly correlated electrons, and indeed, this is a divergency, and that points to what is known as the dielectric catastrophe for strongly correlated electrons. So this is pretty interesting. In any case, we now have the dynamics, the polarization, the polarizability. We can calculate the spectra. So again, this is the experiment, and this is what we calculate. So Raman is not particularly interesting. Look at the infrared. We are able to reproduce this combination bands in terms of band shapes and more or less frequency, and I'm really happy about this result. So we can do anharmonic spectra quite well. And also this again proved that the model works quite well. We can also look at what happens in the region. This was the region of molecular vibrations, 1,000 centimeters or -1. We can go to the lattice phonon region. This is the infrared spectra calculated as a function of temperature. There is, appears the dimerization mode with a huge intensity, but this again was a result that was obtained already in the harmonic approximation. You don't need any anharmonicity to understand what happens here. But you need an harmonicity to understand what happens in Raman spectra, where we calculate the appearance of, with a huge intensity at the transition, of an overtone. Again, the overtone is there because of an harmonicity. And again, we have also an experimental lab, and we were able to locate this combination, overtone band. Indeed, the work on the vibrational spectra of this system started because experimentalists collected these spectra and were not able to understand what this strange bump was. Then I showed up and said, well, this has to be an harmonicity, my favorite. And together with Gabriele, we put on all this machinery for the calculation of vibrational spectra. And we were pretty successful. Okay, now to the real. I hope I have some more. Sorry? Okay, good. So this is actually what I wanted to show you today. Oh, this is unpublished so far, but well. Photo-induced phase transition and ultra-fast excitation. First of all, photo-induced phase transition, we now have the potential energy surface in the close proximity of the neutral ionic phase transition. The system is stable as a neutral, but we have the two metastable states for the ionic dimerized phases. At ambient temperature and at equilibrium, of course, only the stable state is, the thermodynamically stable state is populated, but of course if we shine light, this is not particularly interesting. We excite our system, and once the system is excited, maybe it can go to populate a metastable state, this long-lived metastable state that are the signatures of this photo-induced phase transition. And of course, I will not go into any detail here. There are experimental results about that, mainly from people in Japan, Okamoto, that use optical spectroscopy to demonstrate the presence of a photo-induced phase transition. There are also X-ray data, because again, here we have a dimerized phase, so you can see it from X-ray scattering data. But the experiment I want to discuss today and try to simulate today is this ultra-fast excitation. So what they do is to use on TTF chloranil at this temperature, so very close to the phase transition where metastable states are present, is to use an ultra-fast pump, so 15 femtosecond, extremely fast, and measure, go with the probe, and measure the variation in the reflectivity, so optical properties, optical spectra. And what they get again is this oscillating signal. They are extremely clever, and they can extract a lot of information from experimental data. And one very interesting result, the result that actually made me interested in this kind of work, is that they are able to demonstrate that upon one photon absorption, in the first 20 femtoseconds, so almost vertical, 20 femtoseconds is their resolution, they cannot go shorter. One photon absorbed is able to make 10 dia pair go from neutral to ionic. So one photon moves 10 electrons. This is really impressive. Then They also look in detail at these oscillations, and they are able to see, to decompose the observed oscillations into several oscillations related to the molecular system and to the lattice phonons. And of course, this is more clearly seen in the Fourier transform. So this is 50 centimeter to the minus 1. And then you have several signals, including this signal at around 1,000. But what it is even more interesting is what they call the wavelet analysis. So what they do is to analyze the oscillation as time goes on. And they are able to see how the frequency of concentrate on this mode, the frequency of this mode changes on time. And what they see very clearly is an oscillation of the frequency. So basically, the frequency of the high frequency mode, of the molecular mode, is modulated by another frequency, and it is not really surprising. This frequency is again the lattice mode frequency. And this to me tells again that there is a strong coupling between the two kinds of motion. So there is a strong anharmonicity, really strong, because again we are coupling modes at two different frequency regions, very large difference in frequencies, but we are able to couple the two modes. So it is an harmonicity. And again, I have to fight against the experimentalists because they have a different picture, very complex picture, very complex mechanism for things, which is basically only an harmonicity. I will try to convince you. Okay, so what to do now? I want to simulate a photo-induced phase transition. So I have to go from the ground state potential energy surface to something which is excited. So it is one order of magnitude more complex, but of course I can calculate also the excited state potential energy surface. So this is the ground state, this is the first one, which is also the one with the strongest transition intensity, the strongest oscillator strength. So these are the two surfaces. This is the same picture. It rotates, again to show you how clever I am, no, to show you that there is what you call a conical intersection. But this is very peculiar because this happens in the ground state. So this is the lowest potential energy surface. This is not an excited state. This is ground state. You have this sort of intersection basically because you have a discontinuous phase transition where several diabatic state crosses, and then you have this sort of intersection here. So we are able to vertically populate this state, shining light, and the excitation frequency is in the right order of magnitude. And now what happens? So the point is that so this is a cut, This is a cut of this potential energy surface along delta equal naught where there is exactly the conical intersection. Now, this is the ground state, of course. This is the adiabatic excited state. The idea is how can I populate this state? It is trivial, of course, you know by yourself. If I shine light, the system starts to evolve on this surface, but there it can choose to go into one of the two potential energy surfaces. And of course, to simulate photo-induced phase transition, we are interested in the motion in the diabatic potential energy surfaces, not on the adiabatic ones. So we calculate this adiabatic potential energy surface, and now the point is to construct the relevant diabatic potential energy surfaces. It is a very simple thing here where you have a crossing. It is a little bit more tricky there, where of course what we do is sort of smoothing down, but trust me, we can do that. And we have this is not very easy to see. This is the ground state. This is the diabatic potential energy surface. So our model is that we excite on the diabatic potential energy surface that here coincides with the adiabatic ones, but then the motion goes in the diabatic potential energy surface. And of course, the dynamics is now very easy, and you have Q oscillation at high frequency. Q is the molecular vibration, delta oscillations at low frequency, and you can Fourier transform. And this is the beautiful result. The colors are beautiful, at least. This is my Fourier transform, and this is the wavelet analysis. And you see that I'm able to reproduce very nicely the experimental data. And so I want to stress again, experimentalists, Okamoto group, did a beautiful experiment. The explanation, if you go to their papers, is a very, very complicated one. Actually, it is a very simple explanation for that, and it is an harmonicity, the wild harmonicity that occurs in the close proximity of a phase transition. Okay, now to this multi-electron transfer. As I told you, experimentalists found that in the first 20 femtoseconds, so almost vertical, one photon absorption moves 10 electrons, which is strange and interesting. And we can say something about that, because we have our dynamics in this potential energy surface, and we can calculate many things, Q and delta position, but we can also calculate rho, the amount of charge transfer from the donor to the acceptor. And of course, if I multiply by the number of sites or something similar, I can translate this information. So the system starts as 0.2, as a unicity 0.2. On vertical excitation, go to 0.4, and then it starts oscillating on the potential energy surface, okay? I can translate this information into the number of electrons which are transferred, and the first result is that already at the vertical, more than one single electron is transferred upon absorption of a single photon. And this is, I have no time to go into many details. This was predicted by us in 2003, actually. So well before the experiment, and it is an effect of strong electronic correlations. And this number can be even higher. But what it is even more interesting is that then the system moves immediately along this potential energy surface, and you see that in the first vibrational period, actually in half the first vibrational period, so within 15 femtoseconds approx, or possibly even less, the ionicity becomes pretty large, and the number of transferred electrons becomes very large. Actually, it is of the order of 4. It is not 10. The experimental result, it is 4, but I'm sort of happy about that. So there is this very fast motion on the excited state potential energy surface, which is driven by a combination of electronic correlations from, instead of 1, we have 1.3, and then molecular vibrations coupled to the electrons that drives us towards this number of 4. Again, it is not 10, it is 4, but I'm happy. So this was the last. I can conclude saying that the minimal model, this modified Hubbard model, which has as main ingredients, again, delocalized electrons in 1D, strongly correlated electrons coupled to a soft lattice. This very simple model sustains a lot of physics, of interesting physics, continuous and discontinuous phase transition, lattice relaxation and dimerization in the ionic phase. We have discussed with a lot of details vibrational spectra and photoinduced phase transition, which again is a sort of vibrational spectra in the excited state. I have not touched upon the dielectric anomaly, and I shortly addressed diffuse X-ray scattering, but this is something that the model supports very, very well and quantitatively. And so the take-home message is that the coupling of molecular vibrations and lattice phonons to delocalized and strongly correlated electrons originates a huge harmonicity that has to be taken into account when looking at optical spectra, and several anomalous features that include this multi-electron transfer. And again, that's all. Thank you so much for your kind attention. Oh, sorry. There is something that I always forgot, fans. The reason I want to show you this today, even if I had forgotten initially, is that the fans, I'm lucky. In these days I have sort of some fans, and I want to show you in whatever unit of measure it is, you can guess, the order of magnitude of the funds that comes from European Commission, and then from our Ministry of Education, and then from other sources. And if you look at the order of magnitudes, we can say Rome, we have a problem, I would say. Don't you agree with me? Okay.
I think so. Thank you.
Sorry.
For your exciting data. Are there any questions? Okay.
Maybe you mentioned it at the beginning, but actually, how do you count the electrons when you follow the initial part of the spectrum? How can you establish that you've transferred 1.3 or 4 electrons?
Okay, this
because they are actually bound all the time, so they are never really transferred.
Sorry, I missed the second part of your question.
The electrons are bound all the time, so there's no transfer of electron into the continuum. So you're talking about transfer to another region of the spectrum, or it's a way of describing the phonon coupling?
I will try to address your point. Let's just look at
Yes, no, I've seen that. That's the origin of my question. Maybe you mentioned it before. How do you count the electrons?
Okay. From the calculation, it is pretty simple because I don't know if it was a question for the experimentalist or from the theoretical perspective.
I mean, electrons are actually fermions and they're not distinguishable and they exchange. So which electrons are where,
okay.
It's a matter of
the point
opinion.
is that you have a donor and acceptor molecule in the stack. Okay, and I told in the beginning, depending on the strength of your donor and acceptor molecule, they can bear a different charge. They can have 0 charge, or 0.1, or 0.2, or 0.9.
So it's a complement to the actual physical positive charge, or what? In the experiments, what do you actually measure then?
In the experiment, I can show you what they measure. I hope I have this. Sorry. Oh, I do not remember where I have the figure, but I hope it is here, this animation. Okay. This is one way to calculate the charge that experimentalists have devised. Basically, what they have is the reflectance spectrum of the system in the neutral phase. The neutral phase means that in this case, there is a charge of 0.2 on each molecule. So the donor has plus 0.2 and the acceptor has minus 0.2. When they go in the low temperature phase, 77 K, basically the charge goes to 0.7 or roughly so. So you have 0.7 plus and 0.7 minus. And this means that on average, in each donor receptor pair, 0.5 electrons is transferred. Okay?
No, I understand. So it's just a conventional figurative way. Physically, this doesn't happen. Electrons are not transferred.
Why not?
Because they are localized and they are continuously exchanging with the others. And if you were
but on average, you can, if you look at the vibrational spectrum of this system, you see that the spectrum changes from the spectrum, the vibrational spectrum of a neutral molecule to a vibrational spectrum of an ionic molecule.
Oh, of course. No,
and in this sense,
what you're saying, I'm just saying that physically you cannot transfer electrons because electrons are not individual particles since they are bound all the time. So the convention is actually very useful. That doesn't mean that physically happens. That's all. But I mean,
actually, I've not got the point, but we can discuss it later because no, I feel. But there are so this is real charge transfer going on from a kind of there is a transfer of electronic density from one molecule to another molecule. From one, let's say here we have two sublattices. From one sublattice to the other sublattice, I have a net transfer of charges. And this goes in a temperature-induced phase transition and a pressure-induced phase transition, as well as in this photo-induced phase transition. And we have an enormous...
Let's go to the second question.
I still disagree.
Okay, no problem.
Oh, okay, I would have a number of curiosity, but I think there's no time. So In your dynamics, I can say is a kind of, I don't know, fully coherent dynamics in the sense that you're switching from neutral to ionic, and in all the chain you have this plus, minus, plus, minus, plus, minus. I mean, is there the possibility to have defects, or you can break introducing defects in your dynamics would
actually,
this may appear.
This is a very interesting question, actually, because what I'm doing, actually, even if I'm not told you, is the dynamics around defects. It is a localized excitation, because if it were a delocalized excitation, everything would be smeared out on a huge number of sites. So we decided that our 16 side chains is enough to understand what happens in a localized excitation. So in a sense it is a dynamics occurring on a portion of the chain by definition. However, I've not put it on, but on these slides, because it is too tough, there's not enough time. The dynamics are not only done for the equilibrium position. Actually, we used thermodynamic, let's say, weight of the different states, and so we have the dynamics of several wave packets that sums up to give the total answer, the total response of your system.
Let's go to the second speaker. Second speaker is Alberto Baiardi, and he speaks about fully automated harmonic models in internal coordinates.
Perfect. So this morning I would like to talk about the work we are doing in the group of Pisa to extend our model for computational spectroscopy to the use of internal coordinates. And after explaining why we are interested in the extension of our framework to the use of internal coordinates, I will briefly describe our implementation, and I will present some result about some test case we have chosen to show the reliability of our code. This work is a part of a bigger project which we call the multi-frequency virtual spectrometer, which is a project which we have in our group, which is the build of theoretical analogous of the usual spectrometer which is used in the labs. And we are developing a lot of modules, for example, vibrational spectroscopy, rotational spectroscopy, but today I will focus on the module which is devoted to vibrationally resolved electronic spectroscopy. So electronic spectroscopy in which we can see the vibrational substructure of the spectrum. I will briefly now present the general framework which we have for the Cartesian coordinates case, and then we will extend the framework to internal coordinates. We are able, in our framework, support different kinds of spectroscopies, the most usual one photon absorption and one photon emission, as well their chiroptical counterpart, ACD and CPL, as well also resonant Raman spectroscopy, which is a nonlinear effect. And for all the spectroscopies, we have developed two parallel formulations, which are the sum over states case, which is called also time-independent case, in which you get the overall spectrum by summing up all the single vibronic contribution. And on the other hand, we have also the time-dependent formulation, in which you get the spectrum as a Fourier transform of the appropriate autocorrelation function, which is under the harmonic approximation analytical. So what you have to do is just to calculate the Fourier transform by numerical methods. And this is the level of approximation we will use. We We include mode mixing effect through the so-called Biczysko transformation, which is a linear transformation. And we include both Frank-Condon and Esbert-Teller terms. So we include also first-order terms in the transition dipole moment expansion. And finally, as it has been said yesterday, when you perform vibronic calculation under the harmonic approximation, you can choose two different reference geometries for the final state of the transition. Either you use the equilibrium geometry of the electronic final state, and here you are under the so-called adiabatic model, or you use the equilibrium geometry of the initial state, and then you are in the so-called vertical models. For the Cartesian case, we have implemented both of them. I will stress that for the internal coordinate case, there is a difference between them, and up to now our implementation includes also adiabatic model, but I will go to this point later. Before going into detail of our implementation, I will show you just one example to explain why we want to use internal coordinates for vibronic spectroscopy. This is quite a simple case. It's the phosphorescence spectrum of biphenyl. And here there is the experimental spectrum and the theoretical spectrum calculated at the Frank-Condon level using the adiabatic models. And as you can see here, the agreement between the experimental and theoretical result is very, very poor because there is a huge vibronic progression which is not present in the experimental results. But why is that? If you see the geometry of the two states, the singlet state is twisted while the triplet state is planar. So between the two different electronic states, there is a huge deformation associated to the dihedral angles between the two rings. And at the harmonic level, Cartesian coordinates are not able to describe correctly this kind of deformations. And this has two main effects. First of all, you have additional couplings in the Biczysko matrix at the Cartesian by using Cartesian coordinates, and you have also larger components in the shift vector k in the Biczysko transformation. While if you use internal coordinates, those two drawbacks are expected to disappear because going back to the example I showed before. For example, the deformation associated to the dihedral angles is associated to an internal coordinate, and so you get a more diagonal Biczysko matrix, and the shift vector is now more physically right. But let us start with the simplest set of internal coordinates, which are the so-called primitive internal coordinates. It's the most intuitive from a chemical point of view, because you get all the bond lengths, all the dihedrals, and all the valence angles. But if you want to work with such a set, you have two problems. First of all, and this is a problem which is common to all internal coordinates, they are no linear function of the Cartesian coordinates. And so some drawbacks are present. And the second problem is related to the number of internal coordinates you have, because you have more internal coordinates than you actually need, because the number is greater to the number of degrees of freedom of the molecule. So before performing the vibronic calculation, you have to select a subset of those internal coordinates which is not redundant. The first problem can be easily solved by using the theory of Wilson. You just have to perform the GF method after calculating the Wilson B matrix, which is the first order transformation between the Cartesian and the internal coordinate space. You diagonalize the GF matrix, and then you have the normal modes, which are no more orthogonal with respect to the Cartesian case, but it's just, it's a technical problem but it's quite easy to extend the definition of the Biczysko matrix and of the shift vector to the internal coordinate case. At this point, there is the difference between adiabatic and vertical models in internal coordinates, because for vertical models, to calculate the Hessian away from the minimum point, there are some technical problems because you have a contribution of the derivative of the B matrix and of the gradient, which is not straightforward to take account it. And so up to now we have implemented in our code only adiabatic models. Let us go now to the second problem, which is the selection of the non-redundant space of internal coordinates. And in our implementation, we have included some algorithms which are used in the field of geometry optimization. And the first one is quite simple. It's what are called the so-called delocalized internal coordinates, which are built by diagonalizing the BBT matrix, which is equivalent to perform a singular value decomposition of the B matrix. You take the eigenvector with non-zero eigenvalues, and building this matrix, you get the transformation from the redundant space to the non-redundant space. And I want to stress that even if you use the B matrix to select the non-redundant space, and so we are working in the linearized space, the final coordinates are non-linear, so are still curvilinear. So this is a quite straightforward way to build internal coordinates, because you just have there is just a diagonalization step, and so it has been chosen for us as a reference procedure. So let us go back to the previous case, the phosphorescence of biphenyl. This is the Cartesian case. We have the huge progression which is not present in the experimental data. If you switch back to the Cartesian, to the internal coordinate case, the situation is now better, and you see that you can assign some of the band of the vibronic progression, and so the method seems reliable to predict vibronic spectra of flexible molecules. But if we go back to the definition of the transformation between the redundant and non-redundant space, we see that we have mixings between different types of internal coordinates. And for example, you will get some mixing between angles, dihedrals, and bonds, which is quite an unwanted feature, because we know that large amplitude deformation are usually quite localized on a single type of coordinates and on a single portion of the molecule. So in order to solve this problem, we have implemented also another algorithm which comes from the optimization technique. Okay, if I don't want to mix different types of coordinates, I can diagonalize by using a block procedure in a separate way, performing the singular value decomposition for bond, angles, and dihedrals. This seems easy, but for complex topologies, like for example rings, we have some redundancy which mix angles and dihedrals, for example, and bonds. So in order to have the correct number of internal coordinates at the end of the procedure, you have to do an orthogonalization step for each block. And so at the end, we use, in our code, we have implemented a Gram-Schmidt orthogonalization. At the end, you see that the first block is uncoupled to the other, but you have some coupling in the second block and also in the third block. So yeah, the mixing is limited, but it's not fully cancellated. So a more refined procedure are the so-called natural internal coordinates, which have been proposed more or less 30 years ago by Poulet. And the idea is quite simple. We take all the bond lengths as individual internal coordinates. We reduce local symmetry by taking the appropriate linear combination of valence angle for each non-terminal atom. And for example, if you have planar structure, you have to add an out-of-plane coordinates in order to let the planar structure to move out of the plane. And finally, you have to reduce you perform just a singular value composition on the dihedral space in order to define the relative orientation of the non-terminal atoms. So the advantage is that the coordinates are now high localized. You don't have coupling between different type of coordinates, but particular K must be paid for such complex topologies, for example rings, because you have to define special coordinates like linear combination of the angle and of the dihedral of the cycle, and then you have to fix this coordinate and project out all the other when building the natural internal coordinates. But this is the most accurate model we have implemented in our code, And just to show you the reliability of this last set of internal coordinates, this is another case, is the phosphorescence of aniline. And here the large amplitude motion is the NH2 motion, because the NH2 group is planar only in the triplet state, but is pyramidal in the singlet state. And so if you try to compute the phosphorescence spectrum at the Cartesian level, you get a huge spectrum, very huge vibronic progression. But if you switch to the natural internal coordinates, the agreement between experiment and theory is now remarkable. And I want to stress that we have calculated also the spectrum at the vertical level by using Cartesian coordinates, because it has been shown that vertical model in Cartesian coordinates are usually in agreement with adiabatic model in internal coordinates. And in this case, the result of the vertical gradient model are better than the adiabatic Hessian one. I wanted to compute also the more refined model, vertical Hessian, in which we include also mod mixing effects. But it was quite hard because I had an imaginary frequency and it was hard to decouple it from the others at the Cartesian level. And just a comparison between the natural internal coordinates and the localized internal coordinates. This is the same result as before. I just put also the stick spectrum in order to show the vibronic assignment of all the bands. If you try to compute by using the delocalized internal coordinates, this is the result. The overall band shape is more or less reproduced, but if you try to assign the band, it's more or less impossible because there is a huge progression of low intensity transition, which makes the vibronic assignment more or less impossible. And at the end, I want just to show you a final application, an extension of this framework also to resonance Raman spectroscopy. And as a test case, we have chosen the 5,6 dimethyl uracil, because resonance Raman spectroscopy has interest in the characterization of the dynamic of excited state of nucleobase. And since they are usually flexible, maybe they are test cases to study with the internal coordinates. And in this case, upon excitation, we have a torsion of the methyl group of about 60 degrees. And so there should be a difference between Cartesian and internal coordinates. Those are the results of our simulation, together with the experimental results, which are quite recent. As you can see, both vertical and adiabatic models in Cartesian coordinates does not give a satisfactory agreement with the experimental counterpart. If we switch to the adiabatic case in internal coordinates, the agreement is now better because all the huge bands below 1,000 centimeters minus 1 are no more present. There is still a shift. The spectrum is recorded in water. We did a simulation also by including solvent effect with the PCM model, even if we know that some specific interaction can be relevant for this kind of molecules. And those are the final results. And now, more or less, all the bands are there, and also the intensity match pretty good. So, also in this case, it seems that an appropriate choice of the internal coordinates can be useful to give to simulate the experimental results. And in this case, we have used natural internal coordinates. So to conclude, I've shown you our implementation of internal coordinates and their application to vibronic spectroscopy. And when large amplitude motions are present upon electronic excitation, internal coordinates should be used when adiabatic models are chosen. And thanks to our general implementation, we kind of have applied this framework of internal coordinates to different kinds of spectroscopies, also non-standard one like resonance Raman. And there is still work to do. First of all, we want to extend this framework also to vertical models. I've not said before, especially to the vertical Hessian case in which mod mixing effect is included, because in this case the two sets of coordinates give different results. Furthermore, if the large amplitude motion is active and you see it in the spectrum, since those modes are usually highly anharmonic, we have to develop an harmonic model to treat this number of modes in an accurate way. And finally, we want to integrate this framework also in our implementation of the vibrational perturbation theory to simulate an harmonic vibrational spectra. And I want to thank my two supervisors, Professor Vincenzo Barone and Dr. Julien Benoit, who supported me during this master project, all the Dream subgroup for the environment of work, and all of you for your attention.
Thank you very much.
There is time for a couple of questions. We start from before.
Alberto, congratulations, nice work. About the uracil, no? So you're in resonance with the Piper star state, I guess.
Yeah, that's true.
Now I don't know about the dimethyl uracil, but the Piper star state is not planar, no? In the excited state. So you have if it's true, you have a double well potential, so you have intrinsically a non-harmonic situation. How did you deal with that?
In this case, the deformation, the structure is still planar, so the most important deformation is associated to the methyl group. So we didn't have any problem in the representation of the distortion in the ring deformation normal mode.
Yeah, the question is that if you have a small deformation, you can have it also in the opposite direction. So you have
to choose. No, but in this case, it's planar. It's a minimum even in the planar situation.
That was a very interesting talk. I found the idea of the delocalized internal coordinates very nice. It's a nice way of dealing. But I was wondering if when you do this and you diagonalize and you get the diagonal terms, are they mass weighted in a different way? Because of course, if you delocalize the internal coordinates, there are mass factors in the internal coordinates that get all mixed together, right?
No, because, I use only the BBT, so the mass is not present in the diagonalization. Actually, you can...
But then you pay a price when you calculate the kinetic energy terms.
I have to work in mass-weighted coordinates there.
Because I was wondering if you do keep the masses in some way, then you would recover something which is similar to the local vibrations. You will find that some of these...
because actually it's more complex, the framework, because you can get the non-Adunta space by diagonalization of BABT, where A is a general matrix. And so you can put as A as the inverse of the masses matrix, and then you get the coupled you should get the coupled internal coordinates. And this is more or less what local modes are, but natural internal coordinates, tend to go
I can see that are more useful for you, but I wonder if one bothers to reanalyze them, then you recover local coordinates.
Yeah, but there should be work to do in the definition of the A matrix in the diagonalization of BABT.
Time for Javier Cerezo, solve an effect of the Barone spectra, implicit and explicit models.
Thanks. First of all, I would like to thank the organizers for giving me the opportunity of presenting our work here. That is related to the approach to solvent effects on barbonic spectra by using both implicit and explicit models. So let's start with a couple of words about electronic computational spectroscopy, which nowadays is a technique that provides us with vibrationally resolved electronic spectra, that is not only the band position, but also the line shape. This is very interesting because, on one hand, it gives a lot of help to interpret electronic experimental spectra, and it also provides a nice framework in order to validate electronic structure methods used to perform the simulations. However, there are still some concerns for some systems nowadays in order to reach quantitative agreement. For instance, if we deal with large flexible molecules, we may have to account explicitly for anharmonicity, which is a little bit tough sometimes. And if we are not dealing with gas phase spectra, we need to include the effect of the environment, normally the solvent. The solvent normally affects both the position of the spectra, what is called solvatochromism. This part is normally well described by implicit models, such as the well-accepted PCM, but it also has an effect on the lane shapes. Normally, it results in a broadening of the lane shapes that finally results in structureless bands. Of course, this part can be simulated with empirical parameters, that is, using a defined Gaussian convolution, for instance, so that we have the actual width. However, having a method to have an ab initio method to account for this broadening would give us detailed information between, for the interaction between the solvent and the solid. So it's quite important. To achieve this goal, that is to have a description of the line shape, we have to start with the total Hamiltonian. That includes components that depend on solid coordinates, solvent coordinates, and other terms that are couplings, in the sense that finally in the Hessian we have couplings between the solvent and the solute. The first approximation, we are going to neglect these terms, and in such circumstances the line shape of the whole line shapes because simply the convolution of the independent parts, the solute and the solvent. So as for the solute, this is the red part here, we are going to use the quantum mechanical barbonic calculation that have been just reviewed nicely in the last talk, as we have also implemented in our code FC classes, also time dependent. So pictorially, what we have is that we have our system coordinates, and thanks to this approximation, what we can do is to actually separate the solute and the solvent. As I have just said, the solid coordinates, we treat both problems separately, and for the solid coordinates, we use the quantum mechanical models I just have said. And for instance, in this model example here, that would be this explicit model for the solute that is treated in such a way. For the solvent, we are going to use an implicit model, that is that we don't have the actual nuclei, but only a continuum that reproduce this interaction. In such a case, we don't actually have access to the potential energy surface because we don't have the nuclei. However, by properly selecting the dielectric constant, we can work in two different regimes that are the non-equilibrium and the equilibrium one, that are more or less connected to a kind of Frank-Condon transition and the minimum of the excited state, the final state. The difference energy between the non-equilibrium and equilibrium regimes, that is the solvent reorganization energy, can be connected, for instance, by applying spectral momenta analysis to the standard deviation of the line shape associated to the solvent. And at the end, it just simply depends on the temperature and only in this parameter, the solvent reorganization energy. Therefore, we can propose that the line shape of the solvent to be simply a Gaussian using this standard deviation, and we just simply convolute this Gaussian with our bibronic spectra. So let's review some examples. And we have selected a set of coumarins, which are important dyes for dye-sensitized solar cells. They're important because they have some synthetic versatility, and the photon to current conversion can be actually tuned by the structure. Therefore, actually, this is the set of molecules that we have used for our simulations, and we can see that the efficiency can be around 7-fold increase by properly selecting the derivative. In this sense, computational methods can be key to guide new developments if we are able to provide an accurate prediction of the properties of the dye. From the computational point of view, the availability of a large set of experimental data for the transitions give us a nice benchmark sheet to test our models. First of all, we have computed for all the molecules I showed previously the vibrational structure of the solute. We have used Cambithrolib functional, and so here the results for 0 and 300 Kelvin, and already the vibrational structure of the solute have some differences between the smaller molecules that are these two pink and blue, and the biggest ones. Then we have simulated the solvent-induced broadening by the implicit model I presented just before. So we need to compute the solvent reorganization energy. And as we can see here, this property increases with the size of the dye, more or less. And it also is because there is an increase in the probability change from the initial to the final state. So before continuing, sorry, just a word of caution. We said before that we are considering that the solvent and solid coordinates are independent, and in these circumstances we would expect that the change in this reorganization energy, that is in the final broadening, would not depend that much on the solid coordinates. However, as we can see here, if we go for another point of the potential energy surface, compute again the reorganization energies, we went to the except the state minima. We could have gone to other point. We see that there is a drastic change. So still, a word of caution should be given here. But anyway, we go for the simulated spectra. Of course, we are going to use the data for the ground state minima, which are the ones that are relevant for the absorption, and we obtain that the final results are not that bad. We have more or less, at first sight, we have a generally good performance, as we have combining the vibronic simulation with our broadenings, line shapes that agree quite well with experiment, which is shown here. If we go further in detail, we can see that for the larger molecules, such agreement of the line shape is almost perfect. However, for the smaller molecule, we have this disagreement here. This disagreement also would not be solved if we had a larger Gaussian, because this band is asymmetric. So it seems that we are missing some progressions within our quantum mechanic vibronic calculation. So those are the limits of that uncoupled models, this dependency of this reorganization energy, and also the lack of some vibronic progressions in the spectrum that may appear when we have specific interactions between the solvent and the solute. For instance, hydrogen bonds. So let's review a little bit our assumptions. The first thing we did was to remove this coupling. So maybe we should incorporate it again. But to do so, what we have done, instead of incorporate such a kind of coupling, we have modified our division of the system. And we have moved some solvent molecules from the implicit part to the explicit part, which is treated with the quantum mechanical methods. So again, pictorially, what we are doing is simply transferring some molecules from the implicit to the explicit. So here we can see that we have now, for instance, these two molecules, and this is what we call the cluster models. Again, in this system, we have this super system in which we perform the quantum mechanic vibronic calculation, and the rest of the solvent is treated implicitly with the same method that I have described previously. We can think, okay, why not going a step further and just moving all the molecules to the explicit part? Okay, of course, the answer is quite obvious. Doing so, we had a huge system that could not be treated. Normally we are not going to be able to have the Hessian for such a huge system, but even if we had the Hessian using the time-independent or time-dependent formulation of the vibronic, the quantum mechanic vibronic is not at hand. So still we can do something with this huge system, and it's to treat it classically, so use kind of classical version of the Frank-Condon principle. So we had sampling of the ground state. We had done a molecular dynamics simulation around the ground state in order to generate an ensemble. So we take some snapshot along the dynamics, and for each snapshot we compute the vertical energy. We had an histogram, and that's the histogram that we directly relate with the spectrum. So let's try these models, and now instead of continuing with the coumarins, we are going to shift to this smallest model system that is also able to form hydrogen bonds. And we shift first because it's a smaller system, it's easier to treat these new models, and also because there are, in the recent literature, information about the S0 and S1 solvation dynamics through ab initio molecular dynamics, recently performed by Professor Rega and co-workers. This molecular dynamics was done in the ground anxious state at B3 lib, and we have computed the vertical energies, and also to perform the vibronic calculation of the spectra with PV0. And as I have said before, having the information of this ab initio molecular dynamics is of, well, I think I have time to finish. Yeah, having the information of this solvation dynamics help us first to build the cluster models, which is not a trivial task, because first we need to know how many molecules are we going to include in our cluster model, and where. So having information of the dynamics already tell us that in the ground state there are 3 or 4 molecules surrounding the solute during the dynamics. Most of the time it's going to be 3, so it's the one that we are going to take for further steps. While in the excited state there is a net loss from 1 to 2 water molecules, and we just have 2 molecules surrounding the solid. Another word of caution here is that we are including in our cluster these labil hydrogen bonds, and that would eventually result in a potential energy surface that it's going to be flat and quite rough, so it's completely the opposite to what we want for the harmonic approximation, and we may have some issues there. So just let's go briefly with the results. Here I start with stock shift, because in this case we observe that actually using the cluster model helps us to compute the experimental stock shift. Here we have the experimental is here. We have included also the classic Frank-Condon spectra taken from the snapshot in the ab initio molecular dynamics, and the one with the cluster with 3 and 2 water molecules, as I said before, and with the isolated molecule. As we can see, the isolated molecule, and then the implicit model is not able to provide an accurate prediction of the stock shift. The classic Frank-Condon approximation improved it a little bit, while the cluster model that we have selected recovers almost the exact stock shift. And just to finish, what about the lens shape? Here we can see that as we wanted at the beginning, yeah, we have that the OH progressions that arise during the QM calculation actually increase the width of the spectrum. However, what I'm showing here is that when we increase the number of the molecules in the cluster, we have a huge width here for the 4 water molecules. This is actually a failure of the calculation, because as we can see here, we have compared adiabatic and vertical Hessian models, and they are providing quite different results, and this is a symptom that something is not working with the harmonic approximation, as I have said before. So even though we have this progression that broadens the spectra as expected, we have to be aware of the overestimation for large cluster arising from the failure of the harmonic approximation. And okay, also here we see that for the classical spectra is underestimating the width, but okay, I'm not going to talk more, just show the conclusions. So we have shown roughly 3 models, solid with implicit solvent uncoupled models, which provide a good first approximation to solvent effects. We can use cluster models if we want to include specific interaction, and it can work actually good. Or nearly fully explicit models, but for these models only classical approaches are available, and then we may have some problems in the final result. So we'll finish with acknowledgements. So first of all, my supervisor Fabrizio Santoro, and also from my institute Francisco Avila, who did a lot of work in both the coumarin project and the methylquinolone, and the people from Naples, Nadia Rega, Alessio Pedone, and Greta Donati from the University of Napoli, and Roberto Improta from CNR, who work on the methylquinolone project. Of course, thanks for the funding, and thanks all of you for your attention.
There is time for questions.
Thank you. Very nice talk. I wanted to ask you about the sampling that you used for the AIMD. I saw that you simulated for 10 picoseconds. How large was the system for that simulation?
The actual number of molecules I don't know exactly. It was it is the globe model, so this is a sphere around our solid. It's a sphere of around 10, 11 Armstrong.
Okay, so large. And then the second one, for the calculation of the spectra, you had to take clusters. How many did you take for the simulation? I mean, did you have to average your result over a large number of clusters to have?
What do you mean by cluster?
I mean, if you go a little bit further, you compare the data. You compare the data for 3 molecules of water, 4 molecules of water.
Yeah. But that was for the cluster model. I went a bit fast, but that was a different thing. When we do the dynamics, we had the snapshots, and for each snapshot we compute the vertical energy. It's true that computing the vertical energy, we can also have some cluster in the sense that we can have include in the QM part of the TDDFT also some molecules. Actually, that was also done. It was taken always 3 molecules, I think, for the computation of the TDDFT for absorption and 2 for emission. But let's say that this is important to improve the TDDFT results. But what really matters is that we have this sampling. We took the snapshots and compute the TDDFT. And for the cluster, what we did is that we take the cluster, we optimized, we take the frequency with the implicit model, the PCM. So we have a super molecule that is included in the cavity of PCM. And this is 2 different approaches to have the spectra. With the sampling, what we have is this histogram that at the end we say that this histogram is our our spectrum, while in the case of the cluster model, we actually have a vibronic spectra with all these supermolecules. So in this, we will have this stretching between this oxygen and this hydrogen that would finally give rise to a progression that also broadens the spectra. But in this case, we have the vibronic calculation with the cluster model, what we don't have with the molecular dynamics and the Frank-Condon principle with classical spectra.
Thank you.
Very interesting. I have a question about, you have two different relaxation energies for the absorption, let's say for the ground state or excited state. I feel, I possibly have not got the point, but I feel this is not really a problem. In fact, I would sort of expect this result because in the excited state...
You're talking about this one, is it?
Oh, the one where you have these red results.
Yeah, this one.
In a sense, I would have expected this because after solvent relaxation, you, of course, change a little bit also the state of your molecule. And apart from some understanding that you can get, possibly also from the experimental perspective, if you look at the fluorescence band shapes, usually they are much more resolved than the absorption band shapes, and this goes in the proper direction.
Yeah, I agree. Yeah. First, that would be great to have access to fluorescent data because we had just for the smaller one, and it's more resolved. The only caution that I wanted to stress here is not that, this result is understandable also because there is a change in this polarity difference between initial and final state, and that's what explained. But the conceptual problem that may arise is that having this difference of the simulated solvent effect would in principle be against our first assumption that we are saying that both line shapes are independent. So it's...
My idea, but we can discuss later, of course, is that they are independent in terms of time scales, okay? But basically you have to do an adiabatic approximation for the solvation coordinate with respect to the vibrational coordinates. So basically what you have to imagine is that the vibrational coordinates are always in equilibrium with the solvation coordinate. So there is a dependence.
Yeah. Actually, there is a dependence because we have an electrostatic interaction between the solute and the solvent that is included. But it's just that I saw that this is the excited state minima, which is quite far away, but also it was happening for conformations that were quite close to the ground state. So this gives at least an uncertainty for the prediction, because if our optimization method ends up in a different minima, such small differences actually have not such a big effect, but also kind of effect. So I think it's, at least to wonder about what effect may have.
Thank you again. The last speaker is Elisa Gambuzzi, about sodium and calcium environment in silicated grasses by NMR spectra.
Ecco, ho bisogno per questo perché devo aggrapparlo qua dietro.
Qualcuno che ha più forza?
Va bene, basta che non cada. Non fa niente. Ok. So, I have to change. Can you hear me? I think so. So, good morning to everybody. In this presentation, I'm going to talk about computational NMR spectroscopy, which is intended as molecular dynamic simulation followed by DFT-GPO calculation. And we will couple NMR computational spectroscopy with multi-quantum mass experiments in order to investigate the environment of calcium and sodium in silica-based glasses. And a brief overview. I will introduce you why we are interested in glass structure and what is the problem with the experimental investigation of calcium and sodium environment, and then the importance of adopting a computational approach. I will show you the experimental method and some results. Okay, so why to be obsessed with the investigation of silicate glass structure? Basically because the chemical and physical properties of glasses like diffusivity, bioactivity, etc. are deeply affected by the structure, especially on the short and on the medium range order. And now, glass composition affects in turn glass structure. So, the investigation of glass structure is the key point to build a bridge between glass composition and glass properties, which means it's the key point to develop our design ability for these materials. In this presentation, I will talk about three glasses. There are two aluminosilicate glasses, okay, which are these two, one containing calcium and calcium also or sodium oxide, and one silicate glass containing sodium and calcium oxide. And okay, now what is the problem? The first problem is that we are talking of glasses, and then we are talking of systems which lack of periodicity on the medium range and on the long range environment, and then all those techniques that are very powerful in the characterization of crystalline and ordinate phases like diffraction techniques provide a very few information of these systems. And then the second problem is that calcium and sodium are extra framework cation, and this means that they experience a very variable local environment and they lack of short range order. And then the NMR spectra regarding this extra framework cation are given by the overlapping of all different sites that we can find in the glass, and then they are very difficult to interpret. This is why we need a structural reference which is given by molecular dynamic simulations. Okay. Our method, as I told you before, is a synergetic coupling of experiment and theory. Actually, for each sample, we collect NMR spectra, and for the same composition of the sample, we generate glass structural models, which, of course, have a well-known 3D structure. We compute theoretical counterparts with the DFT-GPO calculation, and then we compare the experiments and the theory. And there are two options. The agreement is not good, and then we have to refine the model, or the agreement is good, and then we can interpret the data, and we can check or elaborate relationship between NMR data and structure. So, now I start to show you some results about the environment of calcium. Okay. These are experimental data, and they are very precious to us because these are experimental data of calcium-43 nucleus. And then this is a very difficult nucleus in some point because the experimental condition required for the acquisition of these spectra can be very expensive in terms of money and also in terms of ability of the operator. And so these are the first multi-quantum mass spectra for these glasses that have been collected in the literature, to the best of our knowledge. And here you can find the distribution of NMR parameter on the isotropic, and on the mass dimension that were extracted from these experimental spectra using an inversion fitting method procedure. And now we have these two precious sets of NMR parameters, and we can extract the distribution. You can see here there are red lines, the distribution for the three classes of quadrupolar coupling constant and isotropic chemical shift for the samples. The black dots are the theoretical counterparts. As you can see, the theoretical counterparts overlap quite well to the experimental data. And then we can say that our structural model reproduced the vast majority of the calcium, of the environments that calcium experiments in the glasses. And then we are confident about the validity of our models. Moreover, as you can see here, okay, the black lines are the experimental spectra again. The red lines are the spectra that we simulated starting from this theoretical distribution. And again, the agreement is quite encouraging. Now, knowing that our models are good and sound, we studied the coordination environment of calcium in the three classes. These three histograms present the population of different coordination sites of calcium in the silicate and in aluminosilicate classes. What you can see is that the distribution here is narrower and here is wider, which is the difference. The difference is that this class doesn't contain aluminum, and then calcium acts as network modifier, which means that it is a depolymerizing agent for the network. While in these classes, the percentage of aluminum oxide is higher and is maximum here, where the distribution is wider. Because here, calcium acts as charge compensator of the residual negative charge that is presented in network when aluminum is added to composition. Okay, it would be very nice if we could extract this kind of information directly from experimental data. And in fact, for decades, experimentalists tried to elaborate simple, effective, univariate correlation between structural parameters and NMR parameters. And what we did was to check whether these correlations were valid for glasses as well. And for example, as you can see here, we plotted calcium oxygen distance versus calcium isotropic chemical shift. They are basically clouds of points. But if you consider each coordination number, then you get reasonable correlation. This means that it exists a bivariate correlation between between isotropic chemical shift, calcium oxygen bond length, and coordination number. And then this is quite challenging, because if you have a reliable set of experimental data regarding isotropic chemical shift of calcium, and you can have an idea about the distribution of coordination numbers, which means the population of the different sites, you can estimate this bond length. Luckily, this was not the case, but because, as I told you before, the experimental spectra of calcium 43 are quite difficult to obtain, and the signal-noise ratio in our cases was not good enough. However, we tried, considering the experimental values of mean isotropic chemical shift that we extracted from the experimental spectra I showed you before, we tried to estimate the bond length adopting an old correlation which was elaborated on crystalline samples, which is this blue line, What you can see is that the bond length is minimum when there is no aluminum in the composition, then when calcium is a network modifier, and is maximum when it acts at network charge compensator. And moreover, now focus on these red dots. The red dots are the data that we obtained from our MD GPO calculation, and as you can see, there is a reasonable agreement between what we find, from the computational point of view, and what we find from the experimental point of view, coupled with previous correlation. And this is all I wanted to show you about calcium, and is that we can estimate the coordination number using the models, and that our structural data intended as the average calcium oxide bond length for the three classes is quite well reproduced. And now I'll show you some results about sodium. And the approach we adopted here was very similar to the one I just showed you about calcium. And in fact, as you can see here, there are the experimental spectra, for the calcium-sodium silicate glass and for the calcium-sodium aluminosilicate glass. Again, for these two spectra, using an inversion fitting procedure, we try to extract the distribution of quadrupolar coupling constant of sodium-23 and isotropic chemical shift. The experimental data are again the dashed lines, and then you see the dots. The dots are the theoretical counterpart. And as you can see, the overlap is not as encouraging as it was in the previous case. Why? In the past work on silicate glasses, where DFT calculations were performed on MD-derived model, the scientists hypothesized that this disagreement was due to the vibrational degrees of freedom of sodium at 300 Kelvin, which is the temperature at which these spectra are collected, more or less, while DFT calculations are basically 0 Kelvin, and then they cannot take into account the degree of the vibrational degree of freedom of sodium. And then this is why we have the disagreement. However, as you can see, okay, the position is not good, but the shape is quite good. The more critical problem is on the quadrupolar coupling constant I mentioned. And then what we tried to do was we tried to scale these values of a factor 0.47. By scaling these values, the agreement was improved a lot, as you can see here. And then, as the scaled theoretical values are well overlapped, or at least better overlapped with respect to the previous scale, to the experimental one, we can use this case value to fit the experimental spectra in order to get a quantification of different sites of sodium, and in particular, I mean sodium coordination numbers. Okay, basically, what did we do? This is the case of the sodium silicate, sodium-calcium silicate glass. Okay, here you can see the theoretical values of isotropic chemical shift and quadrupolar coupling constant for the most populated sites in our MD-derived model, because we cannot consider reliable theoretical calculation based, for example, on a population of 10 atoms. And the most populated coordination sites in the MD-derived models were 5, 6, and 7, which is, I mean, quite reasonable with respect to previous investigations on glasses. And what we did was to use these values, okay, to fit these spectra with the different contribution in order to estimate the experimental population of 5, 6, and 7 coordinated sodium. And what we could calculate was the average coordination number of sodium in this kind of sample, which was 5.5. Again, in good agreement with previous experimental works on glasses. And what I want to point out is that the molecular dynamics model, okay, provided a value of 5.6. So there is a good agreement. And okay, this means that the DFT-GPO calculation are very powerful to interpret spectra and to get information that are almost impossible to get just from an experimental point of view. Very briefly, what I want to show you here is that as we tried for calcium, also for sodium, we tried to check whether univariate simple correlation between structural and NMR feeders existed. The answer was again no, but analogously to calcium, when the different coordination number are considered, you can see that there is a better correlation. I mean, there are not just clouds, meaningless clouds. And okay, I finished also with sodium. I hope I'm on time. And the conclusion is that the DFT-GPO calculation are a very powerful tool to investigate the environment of network modifier cations in glasses. And it has a predictive capacity, because we can estimate coordination number or bond distances from the models when there is no way to have this information just from an experimental point of view, and it's also a good interpretative tool because we can, for example, check whether pre-elaborated correlations are valid on glasses, or we can use the theoretical values as constraint to fit experimental spectra to get some information about structural feeders. And we could get some information that were very difficult to achieve otherwise, I mean, just from an experimental point of view. Now, the acknowledgements. I want to thank Alfonso Pedone, who is my PhD supervisor, Professor Menziani, and our French colleagues, especially Thibaut Charpentier, who is the brain behind the code that allows us to simulate the NMR spectra starting from DFT outputs, and Frédéric Angeli for the experimental spectra. I want to thank Organization for Funding, CEA, the French organization, and the University of Modena, the scientific committee for giving me this opportunity. And of course, I want to thank you for your attention.
For a curiosity than the real questions, are there several isotopes of calcium which you can use for NMR? So it's a question. I know there are many, but I don't know if their abundance or enrichment is possible.
Yes, actually these were enriched samples. It is also possible to, I mean, there are some papers whether it's possible to collect good NMR data from natural abundance sample, but the acquisition times are very long, and we were lucky because we had enriched calcium oxide, and we used it because it's much better, I mean, in terms of quality of the signal that you get.
I was wondering if there is something which can be gained in terms of insight into the structure by measuring different isotopes of the same nucleus, or even by substituting, unusual substitution in biochemistry is cadmium for calcium, and even that, I mean, you could make measurements with different isotopes or even different elements which have very similar
calcium, you mean?
And then fit all the data with your calculations, and this would give you.
Actually, I really have no idea because I'm not an experimentalist, so probably you should
it's more
someone else.
More questions? If not, we can go for coffee. Spero di non averti distrutto. No. Perché è durissimo.
Tell me.
Did you try with ternary system? Because here it's binary, so I know with glass ternary is more challenging.
Yes.
So does it work in this case?
Okay. No. Okay. Was to meet ternary is.
Thank you. Thanks. Okay, good morning. And first of all, I would like to thank you, Enzo, and your collaborators for your kind invitation. And also, I would like to present you my apologies because I just arrived this morning. I would like to discuss with you about some frequency generation spectroscopy and some tools to simulate these spectra and to interpret them. This work started quite long time ago, and it is a multidisciplinary collaboration between theoreticians and experimentalists. And in fact, in this case, the experiments are performed in the University of Namur, in this group with André Permans, Aladin Mani, Paul Thierry, Francesca Secche, Yves Codano, Christophe Imbert, and Dan Lis for the last 15 years. And 4 people from the university, from theoretical group, have been looking at modeling these spectra. So this started in 1997 when I met in the university one of my former physics teaching assistant, André Permans. He was just coming back from, I have some difficulties to see the screen, so I have to come here. Sorry. He was coming back from a postdoc at Orsay, and there he was using this new vibrational spectroscopy called sum frequency generation in order to monitor the adsorption of hydrogen atoms on platinum surface as a function of the electrode potential. And in this experiment, this is the quantity that he was probing. So you see that in the numerator, you have a product of an infrared dipole and a Raman tensor. At the same time, by using theoretical methods, we were interested in calculating vibrational hyperpolarizabilities. And you see that you have a very similar expression because, again, in the numerator, you have this product of an infrared dipole and a polarizability tensor. And in both cases, the quantities are divided by a kind of expression involving vibrational frequencies. So we started to discuss, and we tried to collaborate on this. Is it possible, in a sense, to model these spectra and to try to give some additional information to the experimentalist? And that took a very long time before to write a single paper. In fact, these calculations were done probably around 1999 to 2000, and in this case, this was about this compound called 12,4-nitroanilino-dodecane thiol. So this is a kind of pyranitroaniline with a long alkyl chain on the amino group. And at that time, the first calculation was simply done by using CPHF and TDHF with a kind of a 6311 G star basis set. And without explaining you the details behind this, because I am going to explain you that a bit later, you can see that it was possible to reproduce the experimental data. So I'm really telling here that we were able to reproduce the experimental data and not to make a simulation from scratch to help experimentalists to interpret their data. And the reason was quite simple. We were facing several difficulties in determining these d mu dq, the alpha dq, and vibrational frequencies. In particular, because we started with what I would call the wrong system. Because we have in paranitroaniline, we have a nitro group, and we have these symmetric and asymmetric NO2 stretching vibrations. So what you can see in this table are some vibration frequencies obtained experimentally, either in KBR or on gold surfaces, and the comparison to R3-FOC, NP2, and B3-LIP harmonic frequencies scaled by typical factors. And for several of these modes, what you predict after scaling is not that bad. So you are in quite good agreement with what you observe experimentally, but the problem that is found here in the case of the asymmetric NO2 stretching vibration. You see that if you use R3-FOC, you overestimate the frequency by about 100 wave numbers. If you do MP2, it's even worse, and it gets much better by using B3LIP. And at that time, when we saw that B3LIP and MP2 were not consistent, we say, "Ooh, there is something dangerous here." So we should be quite careful. It was possible, but at the same time, to check that it was coming from electron correlation, and by doing calculation on this nitromethane molecule, it was found that the huge overestimation that you find with MP2 is corrected when you do MP4 calculation. So anyway, at that time we decided that we should start doing some initial simulation, not by using CPHF and TDHF, but at least using B3LIP to get the vibrational frequencies and normal mode. And this is the kind of agreement that we find a bit later in the case of this is a thiophenol molecule on it's either platinum on no, this is silver in this case, and this is the kind of agreement that you can find between theory and experiment. Of course, what we try to do theoretically to improve, I would say, our modeling was also accompanied by some experimental developments. And our colleagues from the physics department in Namur, they moved from the initial experiment performed at Cleo at Orsay by using a free electron laser. They moved to simple laser tables, and in particular they developed a table laser setup. So a very small, I would say, setup to perform experiment, not only at wave numbers corresponding to CH stretching vibrations, but also to go down to this range of wave numbers in order to see some details about the structure of those molecules. So I tell you that this is a good agreement, that best agreement we could find between theory and experiment, and this was achieved by looking at the variation, at the changes of the SFG simulated spectrum as a function of the tilt, so theta angle here, and the Xi rotation angle. So we did this kind of map of SFG spectra. So here you have 3 values for the Xi angle, you have 6 values for the tilt angle, and so you see that there are large variations of the SFG profile as a function of those 2 angles, and the best agreement was found in this case. So we concluded that the orientation of a thiophenol molecule is such that theta is equal to 37 degrees and Xi is about 0. So that was a kind of start and introduction for this work on some frequency generation. But now I think that I should come back to some basic aspects and explain you really what is the some frequency generation phenomenon, and how we could try modeling these spectra. And in SFG, so you have two laser beams. So you have an infrared laser beam and also a UV-Vis laser beam. And these are in phase, and they interact in space and in time. So on the surface with some molecules, in order to generate a new beam at a frequency which corresponds to the sum of the frequency of the incident light. So this is why it's called sum frequency generation. So typically you have here your infrared beam, you have your UV-Vis beam, so you arrive at a virtual excited state, then you have the emission of a photon. So if you have a red and a green photon, you can say that you create a kind of blue photon. What is important, and what is shown already on this picture, is that you see sometimes your infrared beam can be in resonance with a vibrational transition. And in that case, your signal is enhanced. And this is why you see when you do some frequency generation. So typically, you have a fixed UV-Vis frequency, and you scan your infrared beam exactly as what you could do when you do an infrared absorption experiment. Of course, you could also tune the visible frequency, then you can apply the so-called doubly resonant some frequency generation. But this is another phenomenon, and I'm not going to speak about that this morning. So, as a first point, so you see that you have these two lights, infrared and visible or UV light interacting at time and in space. So instead, this is a second order non-optical effect. So if you look at the molecular level, it is associated with a first hyperpolarizability. So here you have the change of dipole moment at the some frequency It's associated with this beta quantity times the field amplitudes, visible and infrared. So if you look at the macroscopic level, so you replace the first hyperpolarizability by the second order nonlinear optical susceptibility Chi2. And of course, in the case of modeling the SFG of surfaces, it will be necessary to characterize the response of the individual molecules in a sense, and then to go to the description of the response of the full surface. What is important to realize right at the beginning is that this is a second order nonlinear optical process. So if it is a second order NLO process, it means that it will vanish in centrosymmetric medium. And this is the strength of SFG, because if you are dealing with a system like an interface, so you have a bulk below, you have some bulk above, and between you have an interface, the two bulks are centrosymmetric, so you have no response from the bulks, but you have a response from the interface. And thanks to these techniques, you can probe the organization of molecules at interfaces. The second thing that you can also see, you have been able to see from the beginning, is that this technique is complementary to infrared and Raman vibrational spectroscopies, and also from the expression you have seen that you have infrared dipoles and Raman tensors entering into the expression of the SFG intensities. In fact, SFG is about 25 years old, a little bit more. And here you have the first SFG spectrum recorded by Shen and co-workers. This was about coumarin molecules on a few silica. These days, SFG is used in many different fields. I have two examples to show you some kinds of application. The first one concern microcontact printing. So you could create functionalized surfaces with alkane thiols, and you can do this by microcontact printing. So you do this, and then what you can look at is the time you need to such that the surface arrives at equilibrium. And if you do your SFG experiment as a function of time after deposition, you see that there is an evolution of the SFG signatures. So here you are in the CH stretch vibrational frequency region. You see that at very small time after deposition, you have quite a complex signature. And if you go to a longer and longer time, you see that your signatures becomes, I would say, a bit more simpler. You have much less peaks in the spectrum. It's easy to interpret this in the sense that when you are at equilibrium, your dodecantiol molecules are mostly in all-trans conformation, and because it's all-trans conformation, all the CH2 of your chains are in a centrosymmetric environment, so you have mostly no response, no signal from the CH2 groups. Only the CH3 group, the terminal CH3 group, is providing some responses. On the other hand, when before equilibrium, your chains might be a bit distorted, you might have some gauge defects, so you lose central symmetry, and in such a case, you see the signals coming from the CH2 groups here, so you have, of course, a symmetric and asymmetric CH2 vibrations signals. I have a second example on this. This is from a work of Sylvie Roque, and she was investigating the organization of surfactants in oil in water droplet, liquid-liquid interfaces. So typically here you have an oil droplet in water, and what you might think is that and that is the case at equilibrium in a sense, you might think that the surfactant molecules should be organized in this way. You have the polaroid, and then you have the alkyl chain. But in fact, this is not what has been found by using SFG. This is the picture that they arrive at the conclusion that this should be this organization, simply because there is a competition between the organization of these molecules and the Brownian motion. So SFG is good to look at the organization of molecules at interface, and this could also be some dynamical structures like these droplets. So the idea we had was to develop some tools to simulate and interpret these spectra, and over the last 15 years we made this at I would say at different levels, and we developed different tools to try going further and further. One thing I would like to mention is that you have a lot of similarities between developing such tools and what you do in the case of other spectroscopies for molecules in solution. And what we have been developing is also connected, but is typically different from what is done by Morita and co-workers by using molecular dynamics simulation. It's also, this approach is also the same as the one used by Marie-Pierre Guégeot, mostly for infrared spectroscopy of air-water interfaces, for instance. Okay, so let's have a look at the formula. So this is the expression of the SFG intensity. And you see that SFG intensity is proportional to the intensity of the two incident lights, and it is proportional to the square of an effective second-order nonlinear susceptibility. So this Chi2 effective. And the effective Chi2 is related to the Chi2 of your interface through the Fresnel factors. So in a sense, Fresnel factors, they connect the external field with the field inside the interface for the different wavelengths. And here you have the expressions for these Fresnel factors. So in the simulations, we are using this model. This is a three-layer model. So you have the substrate. We have some refractive index, and two, we have the interface. We have Ni. This is another refractive index, and then we have here the third medium. So this might be air, but this might be also a liquid. So you have a description of the experiment with the two incident light here, and they could be, of course, P polarized, or they could be S polarized, either the infrared or the visible. So you have some angle of incidence, theta IR and theta vis, and then you have your light at the same frequency with an angle which is fixed by the two other angles and by the frequencies that you are using. Okay, so you understand directly that the interest now is Chi2. We need to calculate at some point Chi2. And by looking at the physics, we can realize rapidly that not all the components, not all the 27 components of Chi2 should be calculated. If your surface is achiral, there are only 4 independent tensor components to calculate. So these are the ZZZ, ZXX, XZX, and XXZ tensor components. So when I'm using these capital letters, I refer to the lap frame. If you do not have mirror symmetry for the molecules that you so at the surface, you need to consider 3 additional tensor components. In a sense, you are dealing with a chiral interface. And I'm going to discuss only these 4 quantities, and they are sufficient to provide the intensity of SFG for different kinds of polarization. So I call these PPP, SSP, SPS, and PSS. So it's important to tell you what's the meaning of this. Of course, it's P and S is for the polarization of the light, but there is an order in this. So when you have PSS, it means that infrared is S polarized, Raman is S polarized, and SFG is P polarized. And this is important because if you change the polarization, you might change a lot the intensities of the light. So these are just the full expression showing that in the case of PPP, you need to calculate the 4 tensor components, whereas in the case of SSP, SPS, and PSS, you only need to calculate one of these. So here are some details about the Fresnel factors. Just to show you that the Fresnel factors, they change a lot as a function of the polarization set or as a function of the considered tensor component, because I would like to come back to this. You see that, you see that to get the effective Chi2, you multiply a given tensor component by 3 of these Fresnel factors. And in this case, the values have been obtained in the case of a platinum surface. So this is a metallic surface. And in order to calculate the Fresnel factors, we have been using all these values for the theta angle, for the wavelengths, and also for the refractive indices. And what do you see? You see first that the largest Fresnel factor is obtained for the ZZZ tensor element. So in the case of PPP polarization, for the other tensor elements, the Fresnel factors are smaller, and in fact they are even much smaller when the polarization of the infrared light is S. So this is simply because your infrared field is damped by the presence of the metal when the polarization is S. Okay? So important when you simulate this, and also with respect to experiment, in the case of metallic surfaces, most of the spectra that are reported in the literature have been obtained with the PPP polarization set, because for the other ones you have small Fresnel factors. So this is for the beginning. So now we need to calculate this Chi2. And to calculate Chi2, we will consider the molecular responses. So the beta responses. And here this is a simple expression in order to go from the molecular to the macroscopic second order NLO response. In the case of here the I, J, and K, I, J, and K, they correspond to the molecular frame. In this simulation, so we need to make this average. We have to consider the way the molecule is oriented on the surface and whether we have some symmetry for the organization of molecules. And the first thing that we assume is that the molecules are arranged in molecular domains. So each time we do the measurement, we look at different molecular domains, and they lead to effective achiral interfaces. So in this way, we need to consider a mirror plane to average the molecular responses in order to get the Chi2 response. The second thing that we assume is that there is the azimuthal angle phi here is distributed randomly, so we need to make an average over phi. What we do not consider is that there is an average for theta and xi, so we consider that theta and xi are more or less fixed. And in the simulation, so what we do is to simulate the spectra for different values of theta and xi. So in a sense, we have a direct delta distribution. And as we have already seen, there is a direct impact of delta and xi on Chi2 and on the effective Chi2. So let's go to the next step now. Oops. Now we need to calculate beta. And in beta, there are two contributions. There is a resonant and a non-resonant contribution. The important part to do vibrational SFG is the resonant part. This is the expression for the resonant part. And so you have a summation over all the vibrational normal modes. as I've shown you already at the beginning of the presentation. And you see the details of this expression where you have the d mu dq associated with infrared intensities and d alpha dq is associated with Raman intensities. So this is the expression that you get in the harmonic approximation, and you see that, of course, if your system is centrosymmetric, if d mu dq is different from 0, d alpha dq is 0, and vice versa. That's why you need non-centrosymmetry to get the SFG signal. So in most of the cases, it is sufficient to work with the resonant beta. We do not need to look too much on the non-resonant beta. But it might be necessary in some cases. And if the resonant beta is typically a vibrational first hyperpolarizability, the non-resonant beta is an electronic first hyperpolarizability. And it could be included in the simulation. And what is important when you do some fit of experimental data is that there might be a dephasing between the electronic and the vibrational beta, and that is included through this phase factor here. Okay, so now in summary, first thing to do consists in calculating the vibrational frequencies, the infrared vectors and Raman tensor. So in this case, you have the resonant beta. You might include a non-resonant beta. Then you do averaging. You get chi2 of the interface, and by considering the Fresnel factors, you end up with the effective chi2, and then you can simulate your spectra and do some simulation and do some interpretation of experimental data. In most of the calculations, so we have been using DFT. As a consequence, there is a question: which functional could we use? Which basis set also to use? And in most of the calculation that I am going to show you, the surface is not explicitly taken into account. At least this is for the first simulation. The second thing that was also done in a few cases, the second medium, so the medium on the top, the medium on top is a liquid, and in such a case, the frequencies and d mu dq and d alpha dqs are evaluated within the PCM scheme. Okay. I do not need this to discuss with you now. Just to tell you, first, we look at different functionals, and at the beginning, we did not find any good reason for not using B3LIP. So we decided at the beginning simply to use B3LIP because it was quite safe. And then for the basis set, we were using a basis set with diffuse and polarization functions. And that was tested by looking at some comparison between theory and experiment for infrared spectra and Raman spectra. There are many of these also in the literatures, and they mostly go in the same direction for the conclusions. So I have a few illustrations to discuss with you. And I would like first to come back on the orientation of dodecantiol molecules on metals. And if you look at the literature, there are many different ways in order to do SFG and then extract the orientation of these molecules. So you can do a direct measurement of the chi2 tensor. Then if you have the full chi2, you can extract the beta, and by some analysis, you end up with the orientation of your dodecantiol molecules. This is not really possible when you're dealing with a metal, so that's limited to insulating surfaces. The second thing that is often used is to compare the intensities of different vibrational modes. And this is often done for metallic surfaces, and the last approach is to compare the intensities obtained with different set of polarizations. And this is what with Francesca we have been doing. So probably it's better to start by looking at the two spectra on the left. So these are SFG spectra of dodecantiol self-assembled monolayers on platinum for PPP and SSP polarization. And of course, because we are in the CH stretch domain, there might be some Fermi resonant peak, but I'm not going to discuss this, just to look at R minus and R plus here. So you have the asymmetric and the symmetric CH3 stretching vibrations. What you can see is that when you go from PPP to SSP, the intensity of the symmetric stretching vibration is decreasing by a factor of 30. If you look at the same experiment in the case of gold, you have a decrease of this intensity by a factor of 10. So what was done was simply to simulate the intensities of this SFG transition in PPP and SSP polarization for different values of the tilt angle and also for different values of the rotation angles. So what you see here is that if you fix your rotation angle to 0 or 60 or mostly to any other value, you have a strong dependence of the ratio of the PPP to SSP intensities as a function of the tilt angle. You remember that experimentally the ratio is 30, so we deduce that the tilt angle of most of the molecules at the surface is 37 degrees. If you do the same for gold, you have a ratio, experimental ratio of 10, and you conclude that the tilt angle for the molecule is 46 degrees. So what we would like to have is not only a value of to deduce the value of the tilt angle, but also to deduce the value of the rotation angle. And to do that, we look at the ratio of these two peaks intensities, and it is about 1.25. So we selected theta is equal to 37 degrees, and we look at the evolution of this ratio of intensities as a function of the rotation angle. Experimentally, it is 1.25, so we deduce that the rotation angle is close to 54 degrees. Why is it possible? Why is it possible to extract this information from this combination of SFG spectra? Simply because if you look at the different modes, the asymmetric and the symmetric CH3 stretching, the infrared dipole and the Raman tensors are oriented differently. So when you change your polarization, sometimes you have a stronger, I would say, combination coupling with the infrared light, and sometimes you have a stronger coupling with the UV light. Second illustration. The molecule which is adsorbed at the surface is a nitro-substituted thiophenol. This is again on platinum and on gold. And I will show you that to consider SFG is not enough. So if you just consider SFG, you see that you have again a reduction of the intensity when you go from PPP to SSP. So typically you have a reduction by a factor of 45. Here you have a reduction by a factor of 10. And you can deduce that the tilt angle is about 60 degrees. What you need to do in this case, in order to get the full information, okay, why? Because if you keep the tilt angle and you change Xi, you cannot extract the value of Xi because Xi does not perturb, that does not modify your SFG spectrum. So what you can do is to combine SFG with reflection absorption infrared spectroscopy, and in such a case you can consider two peaks, the peaks associated with the C and F mode. So you have C and F here, and you can look at the ratio of these two intensities as a function of the rotation angle, and then you can deduce this value. I have a few more examples, but I have no idea about the time. I think that I'm running short of time. Yes? So I can skip this because it's again about the CH3 group. With the exception that what we did was to freeze part of the molecule. So we wanted to know from where is coming the SFG signal, and we find that to have a correct SFG signal for the CH3 group, it's necessary at least to include two CH2 units. The second thing that we did was to look at different functionals, and again, we did not find any good reason of not using B-Trilip. The only difference is obtained with HSE06 functional, but you see that on this scale you do not have much, I would say, quite large variation, only 5 degrees. Recently, we started again, we decided to build a new code, because all these things were mostly done by using some Excel sheet by our colleagues from physics department. So we decided to build a new code to go from the molecular responses to the surface or interface macroscopic response. And this code is able to show you the evolution of the spectrum by changing typically one of these angles manually. So you take a molecule, you change the angle, and you see, I would say, on time, the evolution of the spectrum. This is interface with PyVip2 to look at the vibrational normal modes. And in this first application, we have considered at least a small piece of the surface. So the system is again an alkyl chain, but in this case, it is on a silicon surface. We have been using this functional to take into account dispersion corrections, at least because this has an impact on the orientation of the molecule at the surface. And here is the first application that we made with this code. So you have experiment here from the group of Iwasaki. So what you have to consider is this curve in red, and this is what you obtain theoretically. It's easy to look at the evolution of the spectrum as a function of the polarization. So you have here PPP, SSP, SPS, and PSS. Experimentally, only this one is available. So you see that when you go from PPP to SSP or the other ones, you have a decrease of the intensity by about 4 orders of magnitude. And the change of the spectral profile can be related to the Chi2 elements and directly to the Raman tensor and the infrared dipole. So I'm now at conclusions and outlook. I hope that I've convinced you that SFG, and also in combination with other vibrational spectroscopies, is a very nice and very powerful tool in order to analyze the organization of molecules at interfaces. I hope I have also convinced you that it's possible to develop some tools, some theoretical tools, in order to simulate and interpret these spectra. Of course, many aspects have to be taken into account. By considering systems like those I've shown you, that I would say quite simple, you have I would say easy agreement with experiment, and then you can extract these theta and xi angles, for instance. But we know that we need to go much further in these simulations. And there are at least two major effects that need to be included: anharmonicity effects, and there are many recipes. I do not need to go too far to know these recipes to improve our simulation. Also, disorder effects are important. So we consider direct distribution, so delta distribution for these angles. So we need to introduce some disorder. And we would like also to go towards more elaborated interfaces like phospholipid bilayers. And so this is just an idea of the things that we would like to do, and we started. Because in this case, there is not only a question of the orientation of the molecule, but because you would like to know whether the head is hydrophilic or hydrophobic, but there is also a question of what is the state of protonation, and in this way we could help in the design of sensors. So to finish now, I would like to thank all the collaborators that have been involved in this study, and also these 4 funding agencies: the University of Namur, the FNRS, the Franke Foundation, and the Belgian Science Policy. And thank you very much for your kind attention.
So we have time for questions or comments? Oh, please.
I would say that you could characterize a bulk system with, I would say, traditional nonlinear optical measurement techniques. You would simply measure the second harmonic generation. So that is something that is quite straightforward. In order to use some vibrational sum frequency generation, so the idea is to look at a small part of your system, to look at the interface. I am not aware of studies where the idea was to probe the inside with this technique. For instance, what you can do with this technique is to study the composition of teeth and the impact of fluorination on the structure of teeth. I think this is hydroxyapatite. Hydroxyapatite maybe is the material of the teeth, and you can look at this, but what you get is information on the interface, on the surface. Yes, but with second harmonic generation, you do not have these vibrational signatures. Yes.
I'm wondering if we can learn something using this technique or some other.
In fact, you can combine both. You can typically what you would do first is to do second harmonic generation, because it's a much easier setup to use. And if you get the answer you want, let's say you would like to look at some dynamics of orientation at interfaces, this is enough. But if you want to get into the details of the molecular structures, you need, for instance, vibrational signatures, and then you go to SFG. But SFG is a bigger, I would say, is a bigger setup. I think there is also a factor of 10 for the cost of the apparatus. Typically, you go from, let's say, 10,000 to or 20,000 to 200,000.
Other questions? Maybe I have one question about, you showed that the tilt angle depends, of course, on the surface, the type of surface that you have. And but in your model is not included, if not in this three-layer simplified scheme. So
yes,
we think that by explicitly including the atomistic nature of the surface.
So one thing that we could do, for instance, to look at this from another side, would be to do simply a geometry optimization of functionalized surfaces. And then probably we will see that as a function of the nature of the metal, gold or platinum, you would have a different tilt angle. So, but what we do is not this. So we start from some experimental information coming from SFG, and we compare this to SFG spectra. And the advantage that we have in the case of, I would say, this study, is that the signal is coming from the terminal methyl group. So the terminal methyl group is not interacting really with the metallic surface. So your signal is not polluted by the surface. But of course, what we want to do is to include also the surface in the modeling, because there are also information that might, in the case of more complex system, that might be associated with the bond between the metal and the carbon. Also, like the first example I've shown in the case of hydrogen on platinum. Of course, in that case, you really need to describe the full system correctly.
There are no other. Oh yes, sure.
Just a curiosity. If I understood properly, you have these two lasers. One is the infrared laser, and you can image the resonance with some vibration, and then you have the UV laser. I guess for the UV laser, you want to stay well off of the resonance, or because otherwise, United States process come in play.
Yes and no. yes and no. If you want to do, I would say, traditional SFG, so simply resonant SFG. Of course, you do not want to be in resonance. That's one thing. But if you want to get information from the excited states, you can do doubly resonant some frequency generation, and in that case, you want to be in resonance. And this is exactly what the equivalent of going from normal Raman to resonant Raman. If you have a normal Raman, you probe, I would say, all the modes of your molecule, and when you go to resonant Raman, you probe those modes which are associated with the part of the systems where is sitting the electronic excitation. And you have exactly the same here, but with a difference that what you see is associated with a non-central symmetric structure. And that has been done already experimentally, and you have people who have been developing some equations to simulate this. And so it's really the equivalent of a resonant Raman, plus the infrared tensor.
Other? If not, let's thank Benoit and Nadia for the talks. And
thank you.
Okay, let me thank all the participants and the speaker, and perhaps I shift to Italian for giving you some technical details, because the not Italian speaking people will follow us, so that it is not so important, and these kind of details are quite complicated in English. In realtà sono due cose. Una, che visti i presenti, winter modeling è tradizionalmente fatto a Pisa, tranne alcune eccezioni che a me piacerebbe aumentassero, e quindi volevo sollecitare intenzioni di interesse per l'edizione dell'anno venturo da Milano Bicocca, Napoli, Padova, Modena, Parma e quant'altro. E questo è il motivo per cui l'ho detto in italiano e non in inglese, per non far sentire nessuno ufficialmente obbligato. Spererei davvero, perché diciamo è una conferenza piccola, tranquilla, facile da organizzare, sarebbe carino che non fosse sempre localizzata qua, anche se è abbastanza facile da organizzare qua. La seconda cosa è tecnica. Come avevo detto prima, per il pranzo siamo alla mensa della scuola, per entrare nella quale è necessario avere una user e una password, per cui Monica, che è seduta lì ma che si sposterà là fuori, darà a ciascuno di voi un foglietto con la sua user e la password, giusto? Grazie ancora a tutti e al prossimo anno.